Well, let us continue with the topic that we had been discussing earlier, that was on the synthesis of peptide molecules. Okay. We have done the sequencing, how to know the primary structure, that is how the amino acids are arranged one after another, and then we started the reversal of that, that is how can we make a designed peptide with particular amino acid at specified position. Okay. Now, to do that, let me just briefly go back to what we have said, that in doing a coupling between one amino acid with another one, several things have to be considered. One is because these are all functionally active groups, this one and this one, as well as this amine and this carboxy. What we want is basically make a peptide bond between this one, this carboxy and this amine, this alpha amine. So, our target is this of R as CO NH and then R1 and CO2H. This is the final target. Okay. Now, in order to do that, we want to consider following things. First, there can be coupling between the same molecules, because in the both the molecules amine and carboxy functionality are present. So, that requires what is called protection. So, we should, because we want to have coupling between this carboxy and this amine. So, what we need is to protect this amine first and protect this carboxy. We have introduced last time that what are the types of protection. The types of protection are basically that for amines, I introduced two groups. One is called T-butyl oxycarbonyl TBOC, which is cleavable under acid condition like TFA, trifluoroacetic acid, or HF. And the other group I introduced is what is called a CBZ or CBZ, that is, to be precise, that is NH, CO, O, CH2, pH. Okay. And the BOC is NH, CO, O and then a tertiary butyl. Okay. So, now this CBZ group comes off with hydrogen, palladium, charcoal, then you get the free amine, and here to get the free amine you deprotect with acid, but first remember, first you will get the salt, the TFA salt, and then you have to basify and basify and then remove the TFA and you get the RNH2 free amine. Okay. So, these are the two protecting groups. They are frequently used because one does not affect the other. Okay. And for the carboxy group, what we have said, a very similar type of protecting groups. One protecting group which comes off in acid, that is the T-butyl ester, and this also comes off with TFA, and the other protecting group is benzyl, a very similar one like the earlier one, the CBZ. This also, like CBZ, comes off with palladium, hydrogen, palladium carbon supported hydrogenolysis. Remember, this is hydrogenolysis because the product that comes out is RCOOH, that is the free acid, and you get toluene. So, you are breaking this bond, which is called a lysis. So, this is not hydrogenation, this is hydrogenolysis or hydrogenolysis. Okay. So, these are the things we covered last time. Next is first of all these are the deprotection methods, but I did not say the protection, that how to introduce these groups. Okay. So, there are some slides I can show you here. It is shown that to put the CBG group, you take the amino acid, this is your amino acid which is shown as valine, and you take the, this is called benzyl oxycarbonyl chloride. This is the ester of what is called chloroformic acid. Chloroformic acid, formic acid is HCOOH, and you just replace the hydrogen with chlorine. So, that is the ester of chloroformic acid. This is sometimes called benzyl oxycarbonyl chloride, or it is also known as benzyl chloroformate, okay, as the because it is an ester of chloroformic acid. So, in presence of alkali, because there is HCl that will be liberated. So, you need one equivalent of alkali, and then you get the free acid. Okay. This H plus is to extract the system, because you have a carboxylic acid. So, in presence of alkali, that will be CO2 minus. So, to get the free acid, you have to add the acid and then get the free acid. Okay. So, this is the protection. How do you protect the amine with the reagent? The reagent is, just remember, this is benzyl chloroformate or benzyl oxycarbonyl chloride. For the deep protection, I already have said that this is hydrogen and palladium. It goes to toluene, and so it goes to toluene. The breakage is at the benzylic position. So, that goes to OH, and that is a carbamic acid derivative, and that loses carbon dioxide immediately, and it goes to RNH2. Okay. Very clean reaction, because you do not have any carbon dioxide is just evaporated, is just liberated, that is a gas, and toluene is a high boil is a volatile solvent. So, that you can remove. So, ultimately what is remaining is the amine. For protection of by the T-butyl oxy group, that is TBOC, what you use is, there are many reagents, I am just showing you few of those. The most commonly used is what is called T-butyl TBOC anhydride. This is the T-butyl oxycarbonyl anhydride, because you have a COOCO. So, that is the anhydride portion. So, you, or it is commonly called BOC anhydride. So, you take BOC anhydride, one equivalent, add the amine, you do not have to add any other thing, just in a solvent, and what will happen, this NH2 will attack one of the anhydride carbonyls, the other oxygen takes up the electrons, and then that loses carbon dioxide in a similar way, that loses carbon dioxide, and finally, what you get is the protected T-butyl oxy group. Okay. So, this is not shown here, this will be O minus, then O minus comes back and carbon dioxide is liberated. This is carbonate, now you are getting a carbonate, okay, and that is lost. Ultimately, you get T-butyl alcohol, carbon dioxide, and this TBOC protected amine. And the deep protection is by acid. So, in the acid, what you do? You as I said that if you treat that with organic acid like TFA or anhydrous inorganic acids like HF, what happens here is that H plus, this oxygen is the center for negative charge, because of the donation from the adjacent oxygen and the nitrogen. So, that will be protonated, and after protonation the T-butyl group is lost. We know that T-butyl cation is a very stable cation. So, that is lost, and ultimately that will lose one hydrogen, and what you get is isobutylene as a gas, and then you get H plus, and this carbamic acid derivative, what is the intermediate from this part, that will decarboxylate. You know, carbamic acids are very unstable. So, that will decarboxylate and you get the free amine. So, these are the method of protection and deprotection and the corresponding mechanistic aspects. Next comes the another protecting group. I should also tell you, this is another protecting group which is now routinely used in peptide synthesis, that is called the F-MOC group. F-MOC is, the name is there, 9-fluorinyl methoxycarbonyl chloride, F-MOC, and F-MOC protection is very similar. Actually, this is commercially available. This is nothing but this this is called Nile fluorinyl. So, Nile fluorinyl Nile fluorinyl chloroformate, like earlier benzyl chloroformate. So, this will be 9 fluorinyl. Okay, this has nothing to do with your elemental fluorine. This is the spelling is different. Elemental fluorine has an I here, and in this case this is an aromatic hydrocarbon that is called fluorine, and this is fluorine fluorinyl because this is fluorine, then there is a carbon, and then you have fluorinyl oxo. So, it is a chloroformate again, the same thing like the benzyl chloroformate, and RNH2 attacks this. So, it requires definitely one equivalent of base, because you are releasing one equivalent of HCl. So, the group that is generated is this OCO in HR, and on this part is the fluorine derivative. This is abbreviated as FMOC, like your TBOC, and this is fluorinyl methyl oxycarbonyl. Okay. And this group is little different from the earlier ones, the TBOC or the your hydrogen. This group comes off with aqueous piperidine. Piperidine is a mild organic base. Okay. As I told you that inorganic bases you cannot use, because that will cause a racemization of the alpha center. So, you can use mild basic conditions like this aqueous piperidine. You can use piperidine, and if you use piperidine, what happens? This hydrogen is doubly benzylic because it is a benzylic carbon. So, this is doubly benzylic because there is one aromatic ring here, another aromatic ring there. So, this will be lost very in a facile manner, and the result is that this electron goes to there, and then this electron comes to here, and then this goes out. So, that means you are getting liberation of carbon dioxide, and you get liberation of this. This comes from the fluorine. Okay. This is called methylene fluorine, because you have a methylene group in the fluorine. Now, by the way, this is this fluorinyl group is fluorescence, gives fluorescence. So, it is it's very easy to detect. Its detection limit, that if an amino acid is deprotected or protected, that can be performed by doing by detecting with fluorescence. So, when you do HPLC, if you use a fluorescence detector, then that can immediately tell you how much fluorine has been methylene fluorine has come out if you are doing a deep protection, and you can calculate that this is the number of moles that one should get, and if that is the case, that means the reaction is over. Okay. So, these are the 3 groups. So, one group comes off with acid, another group comes off with hydrogen, and there is a third group, that is this FMOC group that comes out in base condition, organic base, that is piperidine. Okay. So, these are the protecting groups. Now, let us consider now what to do after the protections. Now, your job is, so you have a protection here, this amine NH is protected, and this carboxy is free, and for the other amino acid this amine is free and the carboxy is protected. Okay. Now, what type of protecting group we want to use, that we will discuss later. Let us talk about that, what are the conditions that should be used to have this coupling, that means removal of water. Okay. Last time I said that generally amides, because what you are making is nothing but an amide, because these are involving amino acids, we call it peptide, but these are amides. Amides are usually made from acid chloride, okay, or they can be made from esters, that is also possible, some esters, a methyl ester, and you reflux with a free amine. So, that will definitely go to an amide, but you have to reflux it. Okay. The problem is, if you reflux again, the chances of racemization will happen. So, you cannot raise the temperature very much, that is one restriction. You cannot use acid chloride, where you do not have to reflux, it is a very spontaneous reaction, but last time I told you that that forms an azolactone intermediate, and via azolactone the hydrogen becomes very acidic alpha hydrogen, and there is racemization that takes place. So, acid chloride amine, that reaction to give the amide is ruled out in case of peptide chemistry. So, you have to use a very mild reagent, but it should be also not too mild, so that the carboxy is not activated. You have to activate the carboxy, not too much, but at an optimum level, that is the important thing. Now, what are those activation processes? Acid chloride is ruled out, esterification is ruled out. So, only thing now the other people searched in the 1950s that what type of reagent can activate the acid without and forming the amide bond without racemizing the alpha carbon. And one scientist, John Sheehan, he was at MIT, and MIT, that Massachusetts Institute of Technology. So, he developed a reagent which was called carbodiimides. Now, what is carbodiimide? Carbodiimide is basically you have a C double bond N, it is a diimide, okay. C double bond N, on the other side C double bond N, and one side R, another side is another R, okay. That is called carbodiimide. Okay. Now, these are very good reagents to do the activation of the carboxy and subsequent coupling with the amine. The reagent that John Sheehan used was R equal to cyclohexyl, okay. That means a reduced benzene, cyclohexyl. So, that reagent will be called DCC, dicyclohexyl carbodiimide. Okay. And this DCC, what DCC does, it basically activates the carboxy and makes it a very good Levene group. Instead of the OH, because OH is a bad Levene group unless you protonate it, or you have to convert it into a good Levene group, and DCC or any carbodiimide can do that. So, what happens first, this OH reacts with DCC. Okay. So, what is DCC? Again C double bond N, C double bond N, we will just write here R and R. So, this oxygen reacts with the carbon. The carbon is highly electrophilic because it is flanked by these two imine nitrogens, and one of the nitrogen takes up the electrons, and then subsequently that will take up the proton that is available, because it will release the proton will go to the nitrogen. So, the product is, I write here now, from here to there, let us see what comes out. So, you have R and then NH2, and you have CO and then O, and then you have C. On one side it is now NHR, and on the other side is NR, the double bond is still there. Okay. So, this is the intermediate. Now, what you do, you add. So, once the reaction of the acid and the DCC is over, then you add your amine. If you add the amine, now look at the structure, this is now no longer the carboxy, this is the carbonyl carbon of the earlier carboxylic acid, and this OH is now converted into a system which resembles like urea. It is still not urea, but it is a urea type derivative. Okay. But the thing to notice is that if this goes off, this O minus is highly delocalized, because this O minus can go here and this can take the N minus, and then this minus can come back and forth. So, this is a very good Levene group. Both are very highly electronegative. So, this is pulling electrons from the carbon, and so the carbon wants the electrons from the oxygen, and the oxygen now wants the electron from this carbon oxygen bond. So, the basic fact ultimately that the bottom line is that this has become a very good Levene group. So, RNH2 now goes and attacks the carbon, and this goes out. This is exactly the reaction that takes place. So, what you are getting R NH2 and CO NH. Now, remember this RNH2 I have abbreviated it. This RNH2 now represents the NH2 of the other amino acid. So, but in this case I just wrote R, simply R, but that resembles, suppose make it R1 NH2, okay, to make that it's different from the 2 R's. So, you get this your desired peptide bond if this happens to be an amino acid. And what comes out here, that is also interesting. So, you get one equivalent of this C double bond O NHR and NHR. This is nothing but an urea derivative. This is called DCU, dicyclohexyl urea. Dicyclohexyl urea. Urea is only NH2, NH2. Okay. So, let us go to the next page. Now, once we have the DCC coupling over, now I just write all the steps. Suppose I want to make alanine and valine, this dipeptide. So, what I will do? I will first take alanine and alanine amine I will protect with, suppose I protect with T-butyl. So, T-Boc, and this acid is free, and then I take the valine where the valine carbox is protected. Which protection I should use? I should use the same protection or the protecting group which comes, I should use a protecting group which comes under the same condition as the protecting group on the nitrogen of the other amino acid. Okay. So, I hope that means I take a group here which comes off under a condition that also takes up the protecting group of the other amino acid. Okay. So, that I do not have to repeat steps, that will cut down my steps. So, I should use this T-Boc, I know this comes up in TFA. So, here I take a T-butyl and then this is NH2. So, then I add this DCC and I do the coupling CH3, NH, T-Boc and then CO. Now, that will form the peptide and then this will be the valine part. And what is the last step? The last step is deep protection with TFA. So, you get alanine and valine. Okay. Now, question is it the end of the story, the peptide synthesis? Certainly not. There are other important points that we have to now consider. One point is, let me check whether it is here. I think the mechanism in the slide, you can see the in the slide you can see the mechanism whatever I have written. The DCU comes off. Problem 1 is the DCU. What are the problems with DCC coupling? DCU, that is generated as one equivalent, 1 mole equivalent. Okay. That is the byproduct. Okay. That means, you have a separation process now. You have to separate your protected, this is the protected dipeptide from the DCU. Now, luckily DCU is insoluble, has less solubility in dichloromethane. So, you can separate most of the DCU by just crystallization from dichloromethane or methylene chloride. Still there are some DCUs left in that procedure, and sometimes it is really difficult to separate the protected dipeptide or protected peptide from the DCU. So, you have to do series of columns or series of crystallizations in order to get the DCU out. Now, that problem has been taken care of a reagent which is called EDC. That is also a carbodiamide. The theory is like this, that if you have C double bond N, C double bond N, in one arm you have one type of alkyl group, and in the other arm what you do, you put an amine functionality. But that is your tertiary amine. Okay. So, if that happens, then then the reaction will take place like the earlier one, like what DCC does, but the end product here will be C double bond O and urea, which is having a amine group, sorry, CO, then another NH, which is having an amine group at the end. And this amine group, now this will be soluble in dilute HCl. So, if you just give a wash with dilute HCl, the derivative from EDC, the urea derivative coming from EDC will go out. So, that is a good, when you have problems with DCU, you can use EDC. However, this is a much costlier agent than DCC. DCC is much cheaper. Okay, so, that is one problem which can be taken care of by other coupling agents. Another problem that is more serious, and that is the DCU also can give rise to isomerization, that racemization, exactly in the same way like your azolactone formation. Suppose you have this T-butyroxycarbonyl, T-BOC, and when you activate the carboxy with DCC, the intermediate that you get is this NHR double bond N and this is R. This is the intermediate, this is your alpha hydrogen. You want to retain that it's never get lost, otherwise there will be racemization. But this is also a very quite reactive, unlike the acid chloride, it is not so reactive, but you want not a you want less than 0.1% of racemization, that means virtually no racemization, because ultimately these peptides you are making for biological study. So, you have to ensure that my molecule is optically pure. Okay. So, however, what happens in DCC, that there is this azolactone formation, it is the same that comes here. So, that gives you azolactone, and when azolactone formation takes place, you know this hydrogen becomes acidic, more acidic. So, there is some racemization in DCC coupling. So, what to do? Then people thought about it and they could find other protecting reagents along with DCC. If you use that, then this racemization can be suppressed. And what is that? That you take DCC plus another molecule which is quite nucleophilic. This is called 1-hydroxy benzotriazole, hydroxybenzotriazole. Okay. HBT, we generally HBT or HOBT, I think this is the one, HOBT we use, hydroxybenzotriazole. Okay. So, what happens here, that as soon as this intermediate is formed, 1-hydroxybenzotriazole now comes instead of the amine which is going to attack the carbonyl and make the peptide bond. This 1-hydroxybenzotriazole that comes and attacks the carbonyl and kicks out the DCC part, that part is kicked out as the urea. So, what you get is this what you get is this is T-butyl and you will get C double bond O, then O, then N, then there are 3 N's, double bond N. So, you will get this as the intermediate. Now, this is reactive, this does not form azolactone. So, before the azolactone is formed, you form this compound. So, this acts as a nucleophile, and then what happens, your other amino acid that you add as the protected acid, and this amine will now come attack the carbonyl and this goes out. So, you see the N-hydroxy, that hydroxybenzotriazole is again liberated and you can use it in catalytic amount. So, DCC and then 1-hydroxy bench triazole you can use in catalytic amount, okay, because you are releasing the 1-hydroxy bench triazole. But in practice, sometimes we say that to suppress this racemization, it's better that you use 1 equivalent of 1-hydroxy bench triazole, because if it is catalytic, by the time that catalytic reaction takes place, there may be some azolactone formation. So, it is wise to use 1 equivalent of this. So, that is the coupling agent DCC, HOBT, but I said again, if DCU creates a problem, you have EDC, that is an amine group at one of the arm, a tertiary amine group. So, that is called water soluble carbodiamide reagents. You just wash out with actually not water, but with slightly acidic water, you can wash that out, and to suppress the racemization you use DCC along with HOBT, but there are now various variations, other type of reagents, many coupling reagents are available now, and we will do that in the next session. Thank you.